Mention the phrase quantum computing, and the conversation usually drifts toward dense calculus and blackboard-filling equations that feel entirely inaccessible to the casual observer. Our current computers, from the smartphone in your pocket to the largest supercomputers on Earth, rely on a simple binary logic. They operate by flipping microscopic switches between true or false, a 1 or a 0. But squeezing those binary switches into smaller spaces is hitting the absolute limits of physics. Certain classes of massive problems remain completely unsolvable for a system that can only calculate one possibility at a time. Understanding the next era of computing requires looking past the arithmetic. We have to trade long division for a new visual logic. A quantum machine functions as something other than a faster calculator. It operates as an architecture built on a different way of defining a state of being. Think of classical computer logic like a coin resting flat on a table. It exists in an absolute, unmoving state. It is either heads or it is tails. To solve a maze, a classical machine acts as a single line, retracting when it hits a dead end. Quantum logic uses superposition. Existing as a blur of probability, the wave occupies multiple logical pathways at once, identifying the exact exit simultaneously. Superposition replaces the brute force sequence of testing paths over time with a simultaneous state of possibilities. It bypasses the need for traditional counting entirely. Having individual points of probability isn't enough to compute a complex problem. For a system to be useful, those probabilities must interact. This interaction is governed by entanglement, a rule where two separate objects become so linked they share a logical fate, regardless of physical distance. A barrier drops, but altering one entity logically dictates the other, maintaining perfect synchronization without any physical connection. This creates a unified web of probability. It allows millions of separate logical parts to operate instantly as a single, indivisible entity. If the system holds millions of simultaneous probabilities at once, how do we isolate the one result we actually need? We use interference. Interference is the process of choreographing these overlapping probabilities so they collide with each other in a controlled way. In this collision, incorrect paths and contradicting probabilities cancel each other out. Much like noise-canceling headphones, the wrong answers disappear. Only the correct path amplifies itself through this collision, leaving a singular, clear answer without the machine ever performing a traditional calculation. Quantum logic doesn't calculate the right answer. It manipulates the environment so that all wrong answers eventually destroy themselves. Quantum computers are not just faster versions of the machines we have. They're an entirely distinct species, built to answer different types of questions. This logic allows for the simulation of complex natural molecules and the prediction of protein folding, the process where a protein chain takes on the specific 3D shape that determines its biological function. This has immediate security implications. Our current global cryptography relies on the fact that binary machines take centuries to solve certain math problems. Quantum logic renders that encryption obsolete by collapsing millions of possibilities into a single answer in minutes. When we separate the underlying logic from the advanced mathematics, the future of this technology becomes a concept anyone can grasp. It simply requires us to stop viewing the world strictly in binary terms. Navigating this transition ultimately requires philosophical flexibility rather than mathematical genius.